Okay, good afternoon. Now this is week 4 for our signals and systems course. And last week we talked about Fourier series. And today we will continue and we will also start Fourier transform. So conceptually, what is Fourier series? What is it good for? I mean, why do we use it? Or how does it come up? Can somebody explain that to me? Why Fourier series? Yes. So that's the idea. So as we said in the first week of the course, in signals and systems, we look at the nature as collection of two things. We have signals and we have systems. Okay? This is a very general concept. It could be just anything around you is just a combination of these two things. Then we start talking about special kinds of systems, okay? Because when it is just very general, you cannot do much about it. Why? As engineers and scientists, we have to translate the nature into mathematics and write it on a paper and do things on the paper and make some design, then just put it together, manufacture it, and plug it into nature, right? That's how we go around our business. So when we stay too general and too vague, we cannot make any progress. So therefore, for systems, what did we do? We said we talk about some special classes of systems. Like what? What is a special class of systems? Very important, right? What is that? When we talk about system, we talk about some kind of system. What kind of systems we talk about? Linear systems. Then we say linear time invariant systems, right? So we talk about all these things. So linear systems is a very, very special kind of systems in the domain of systems in general. And when we talk about linear and time invariant system, it's even much more special. So we know a lot about that. So when we talk about signals as well, we also start talking about special signals. Okay, we start talking about very special kinds of signals. Like what? What special signals did we talk about until now? Which signals did we introduce? Come on. Okay, what signals did you learn in this course? Impulse, right? Impulse function as a signal, right? What was impulse function? So signals. So it's good to look back every once in a while. So this signal we represent it like that. And this is defined. What was the definition of this? This is 0 when t is different from 0, and its integral is 1. Okay? So what is its value at 1? That's infinite, but it's not arbitrary into infinite. It is just defined this way. Okay? This is the impulse function. As a matter of fact, we build a world around this, isn't it? So what did we do? We said that take any linear time invariant system, okay? And you say you have a system, linear time invariant system, when the impulse is the input, what did we call the output? What do we call this? What? What response? What response? Impulse response, right? So this is a very special kind of signal, and this is called the impulse response of the system. Okay? So this impulse response, and impulse is like a key to open the system theory. Okay? Then what did we say? In the second week, what did we prove? We proved that if you know the impulse response of your system, assume that you have a system, you know it is linear time invariant, and you use the impulse as your input, and you measure the output from 0 to infinity. You know all of the values. So you have h of t. Okay, so you obtain somehow h of t, or I gave that to you. Then if I give you any other input, so for any input, x of t, what is the output? How do we, if you know the impulse response of that system, what is the response of the system to any signal? How do I obtain that? What was it? Please, you know this. What? Yt, okay, what is Yt? Yt is equal to what? Huh? Convolution, okay, what is that? Integral from minus infinity, raise your voice. Okay, x tau. Or okay, so knowing the impulse response of a system tells you everything about the system. If you know how your system responds to an impulse, if it is a linear time invariant system, you know how it responds to any input. Isn't this a very beautiful result? That's why we talk about working with special kinds of system is important. So since we know this linear time invariant system, knowing the impulse response of the system tells you everything about the system, okay? That's one. What other special signals did we learn about? So we are talking about now signals, right? So we said that in this course and the rest of your profession, you will mostly talk about linear time invariant systems, okay? Why? Because we know how to do things with it, okay? And we will approximate anything else with linear time invariant system somehow, okay? What other special signals did we learn about? I know you know it. What? Sinusoids. We learned about sinusoids. We said that, how about, so sinusoids. We said that if my signal is like a sine some omega 0 t, if there's something like this, okay? So we talked about this, and this is what is the beauty of these sinusoids? What are they? Number one property is periodic, right? They are periodic signals, okay? So then after that we said, how about if you have a periodic signal that is not sinusoid? What can we do? So if I have sinusoid, it's of course periodic. And what is the period of this? 2 pi. How do you know that? You don't have to memorize it, right? So this omega 0 capital T should be 2 pi. Okay, it's at 0 and 2 pi. Okay. Then we said, how about sinusoids. How about periodic signals? Signals other than so how do we define them? We said x t plus capital T is equal to xt for one t or for how many t's? When should this be satisfied to call it periodic? What? For all t. For all t. Okay? How do we write this mathematically? We say for all t means this. Okay. So then this is periodic. Of course, this sinusoid sine t is periodic. And what is the period? Period is 2 pi. How about 4 pi? Is this periodic with 4 pi? 6 pi? 7 pi? No. So it is periodic with 2 pi and its multiples, right? So the smallest of such period is called what? Fundamental period, yes. So the smallest of the periods a function has is called the fundamental period of that function. So let's say this t is the fundamental period of our x. Then last week, what did we talk about? We said that, okay, if this is periodic, like we did for functions in general, if you have a function that is not polynomial, we said we can write it as a polynomial, and we came up with Taylor series expansion, isn't it? So here we do the same thing. We say that, okay, in the same manner, if I have a periodic function, can I write this as a linear combination of lots of sinusoids? Okay? The answer turned out to be yes, and the answer was, it's called Fourier series. So if xt satisfies this, then we said that you can write this as xt is equal to a0 plus n equal from 1 to infinity an cosine omega 0 t cosine n omega 0 t plus n equal from 1 to infinity bn sine n omega 0 t. As a matter of fact, we pose this question. Okay, can I write this in this form, right? That's the question we asked. If we do, how should I pick these A0 and ANs and BNs? What did we do to find them out? We said, let's take, since this is a periodic function, let's take integral of both sides on a period, right? So what do you get? So when you take integral of both sides, by the way, why am I repeating this? Is because this is beginning of electrical engineering, electronics engineering, okay? Fourier series, understanding what is spectrum, what is frequency, is the basic stepping stone into electrical engineering. So it is so very much important. I should talk about this every week until everybody in the class listens to me and understands it. Okay? That's why I will talk about it again. And I will make sure you understood this in the exams as well. So it is very, very important. So take integral of both sides. If they are going to be equal, right, you take integral over a period. T. So this is going to be equal to A0 dt integral Okay. What happens to these integrals? Integral of cosine omega 0 t over a period, what is it? 0. How about cosine 2 omega 0 t? It is 0 twice, right? 3 omega 0 t, it is 0 3 times. Goes up and down, and it just cancels. This is also 0. So what remains is that, and what is this integral equal to? What is the integral over period of t? A0 times. So this is a general way of writing it. But how do we write this? Say minus t over 2 to plus t over 2, right? It's the same thing. This is just one way of covering the period. It could be from 0 to t as well. It wouldn't change anything. But writing it symmetric is more useful, okay? So this is 0. This is 0 for all n. And this is just minus t over 2 to plus t over 2 xt dt is equal to a0 t. In other words, a0 is equal to 1 over t minus t over 2 to plus t over 2 xt dt. And what is the interpretation of this? This is the average magnitude of the signal, isn't it? Okay. So how do I compute AN and BN? What do I do for that? This time I multiply both sides by cosine m omega 0 t. Then I calculate integrals. I will find out that all of the integrals will be 0 except when n and m are equal, so all the summations goes away, etc. So I will now do that in the complex Fourier series case. So when xt plus capital T is equal to xt for all t, then there is another way, and this course will be mostly based on this way, and they are equivalent as we showed it to you. You can write this as n equal from minus infinity to plus infinity Cn e to the j n omega 0 t. Okay? This is called the complex Fourier series. Okay. So we do the same thing here. You multiply both sides by e to the, let's say, minus j m omega 0 t, and take integral of this from over a period. Take integral of this. Okay. So you take this, multiply it with the same quantity, and take integral of both sides, so equality is preserved, right? So here, yes, you are now getting used to that. You do a trick. You just remove this, okay? No need. Okay. Then interchange and the summation and the integral. So what do you get? This becomes n equal from minus infinity to plus infinity Cn integral from minus t over 2 to plus t over 2 e to the j. Can I bring them under one exponent? E to the j n minus m omega 0 t dt. Now let's look at this integral. As a matter of fact, it is so simple that we can just do it here. So what is this integral? 1 over j n minus m omega 0 e to the j n minus m omega 0 t from minus infinity to plus infinity, right? Let's just take this for any m, okay? Let's forget about this now. Assume, of course, n is different from m. If n is equal to m, what do you have here? No, and if n equal to m, this is just 1. This is t, right? So we separate it. So this is, when n equal different from what is the value of this one? E to the j, what is this? Minus t over 2 or to plus t over 2? I'm sorry. What is the value of that one? So in the upper limit, it is e to the j n minus m omega 0 t over 2 minus e to the j n minus m omega 0 minus t over 2. What is this? Omega 0 t. 2 pi. And then divided by 2, it is pi. And this is just, when n is different from m, this is just an integer. So what is e to the j, let's call it L pi. What is the value of that? It is either minus 1 or plus 1, right? So e to the j and m pi. And what is this one? E to the j minus pi, because of this minus. Okay? So this is e to the, so this is minus 1 to the power n minus 1, and this is minus 1 to the power n minus m again, right? So this is 0. E to the pi and e to the minus pi, both of them are minus 1. E to the 2 pi and e to the minus 2 pi, both of them are 1, and they always cancel each other. So therefore, all these infinitely many terms, they will give you 0 unless n is equal to m. So when n is equal to, so if n is different from m, all these terms are 0. All terms are 0. If n is equal to m, then this summation becomes Cn, and what is this integral? Minus t over 2 to plus t over 2 dt. What is that? Cn times t. So then what did we have? What we had is that, okay, let me call this m, since this side is m. It doesn't matter, it's dummy variable again, right? So t times Cm is equal to minus t over 2 to plus t over 2 xt e to the minus j m omega 0 t dt. In other words, you just divide it here. Okay, this is complex Fourier series. So this is like a summary of what we did last week. Now we are going to build on this. We are going to further analyze this and discover some beautiful properties.
I didn't understand why it canceled each other.
Why? This is, okay, let me make it more clear. Okay, so you have e to the j. Thank you very much for asking when you don't understand something. I really appreciate that. Okay, so I can just take common with this. What do I have? E to the j n minus m pi 1 minus e to the minus j 2 n minus m pi. Okay? What is this? E to the j minus j 2 n minus m pi. So now it's multiple of pi. So what is it? It is 1. It doesn't matter. It is e to the minus j n minus m 2 pi. Okay, but why? Because I have to common with this one, right? So this is, because of 2 pi, this is always 1, right? It's 2 pi or minus 2 pi or 4 pi or 6 pi, right? So this is 0. So it is 0. Okay. Any other question, please? There is no silly question. You can ask this now, but if you were to ask this after your third year, it would be a shameful thing. You should still ask, but you should ask it in private in that case. Now you can ask it loud and clear, no problem. Okay? So we have now two types of Fourier series. We have one is here. That is traditionally the first one. Okay? So you are working, you have a real function, right? It's natural that why should I look for a complex function equivalent of my real function, okay? So I have x of t, which is a real function. Why don't I write this in terms of sines and cosines? E to the j omega 0 t is a complex unit. So why should I do it? So that's why historically that's the first thing that is done. That was done, okay? I didn't write the result, right? Did I write it? Let me write it here because we'll use it. So an is equal to 1 over t from minus 2 over 2 to plus 2 over 2. Xt cosine n omega 0 t, and bn is equal to 1 over t minus 2 over 2 to plus 2 over 2 xt sine n omega 0 t. And a0 is a0, what was a0? So 1 over t minus 2 over 2 to plus. Okay. This is 2 over t. So when you rely on your memory, it can always fail you. You should always know where it is coming from, right? Where is that coming from? Because you have a cosine square here. Cosine square n omega, cosine square n omega 0 t. Then you say, you remember the derivation with it, then you say 1 minus 2 cosine 2n cosine 0 t over 2. So that 2 comes here, okay? Good. So we have now, for a periodic function, we have Fourier series expansion in terms of sines and cosines. And here we have Fourier series expansion, complex Fourier series expansion. We just have one coefficient that runs from minus infinity to plus infinity. Okay, what is the relationship between the two? So as you will now, we did last week, but let's just review it again. We can very easily find the connection between the two, right? So when you have x of t is equal to n equal from minus infinity to plus infinity cn e to the j n omega 0 t, you can just write this as c0 when n is equal to 0, and then you write n equal from minus infinity to minus 1 cn e to the j n omega 0 t plus n equal from 1 to infinity cn e to the j n omega 0 t. Now here let me just replace n by minus m. This n is dummy variable, isn't it? I can call it n, l, k, any letter I want. So I want to make a change of variable here, replace n with minus m. Then what happens? This becomes equal to z0 plus, and this summation we would go from m equal from 1 to infinity, c minus m, e to the minus j m omega 0 t, plus that remains as it is. This would be a good question in the exam. Simple and nice, but it makes sure that you understood Fourier series expansion and the relationship, okay? So, would you mind I again call this n? Does it make any difference? Okay, this is just n or m or what, it is dummy variable, isn't it? So let me bring them under the same summation, C0, n equal from 1 to infinity, c minus n, e to the minus j n omega 0 t, plus cn e to the j n omega 0 t. Okay? Now let me expand this using Euler's identity. So what is that? C0 plus, so c minus n times cosine n omega 0 t plus, so minus, because of this minus, j sine n omega 0 t. And this one, cn cosine n omega 0 t plus j sine n omega 0 t. Right? Now I have cosine omega 0 t, another one here. Okay, let me regroup this. Then what do I have? C0 plus n equal from 1 to infinity. Can you please tell me the coefficient of cosine n omega 0 t and sine n omega 0 t? So what is this, please? C minus n plus cn. Great. And this one? What? Minus j. Minus j times c minus n plus j times cn. As a matter of fact, I can bring this out here. Okay? So this minus cn plus minus c minus n plus cn. Right? By the way, let's look into this cn business. Just 1 minute. Okay? So what was cn? Cn was equal to, it is written there, where, so it is from minus t over 2 to plus t over 2, xt e to the minus j n omega 0 t dt, isn't it? So what is c minus n? What do I do here? I just replace n by minus n, isn't it? What is that? That is equal to minus t over 2 over t over 2 xt. And this is going to be what? What is it going to be? Minus e to the j n omega 0 t dt. On the other hand, let me calculate complex conjugate of Cn. It's a complex number, isn't it? So what is this equal to? Complex conjugate of this integral. Integral is a summation, right? If you have a number of, please everybody listen to me. Remove the phones, put them aside. Phone is not allowed in this class, okay? Everybody, please listen to me. So when you have a summation and you have zillions of terms in your summation, and you are taking complex conjugate of your summation. It is the same as adding the complex conjugate of the terms, right? So you can say I have Z1 plus Z2 plus Z3 complex conjugate is equal to Z1 complex conjugate plus Z2 complex conjugate. As a matter of fact, not for 3. Even if it is an infinite sum, this is still true. Integral is also an infinite sum, if you remember. So therefore, when you are taking complex conjugate of that, that would mean you can just move complex conjugate inside. So this is a real function, isn't it? It's complex conjugate of this. It's real anyway. It doesn't make any difference. Then it's complex conjugate of that. So what is that? You just replace, what does complex conjugate mean? I told you that last week or the week. You just replace J with minus J. Whatever is the expression, okay? Just replace J with minus J. You obtain. So what does that mean? That means so from these two, what is the conclusion? What do you conclude exactly from these two? So we calculated here C minus N, we obtained this one. Here we just calculate the complex conjugate of Cn, we obtain this. Are they different? So what is the conclusion? They are? Yes. For under what condition? C minus N is equal to Cn complex conjugate. Under what condition? What is the condition? X of t is real. If x of t is real, if x of t is real, is a real function. Okay? If x of t is a real function, this is satisfied. Okay. So, why did I do that? Because this will mean something here. Okay? Let me now clean this so that I can continue my example. This was just a side note. And it's in the video, so you can look it up afterwards. So, let's continue here. So, by definition, what would you have when you compare this with this series expansion? So you are comparing now this and this, isn't it? What can you tell me about A0 and C0? So they are the expansion of these are both equal to x of t, right? This is x of t. They are equal, right? So A0 is equal to C0. Good. Then what do you have? C minus N plus Cn. What is this equal to? It is cosine n omega. It is An, right? And what is the other one? J times C minus Cn plus Cn is equal to Bn. So this is the relationship. As a matter of fact, from here, if you multiply the first, so C minus N plus Cn is equal to An, multiply the second one by minus J, then you have here, so multiply with minus J, you have minus J squared times minus Cn, then plus, so this is minus J squared times Cn is equal to minus J squared times Bn, right?
May I ask you something?
Yes, please.
Why isn't it 0 minus Cn plus Cn?
Excuse me?
Why isn't it 0
At 0, we already calculated that.
J
This,
minus Cn plus Cn.
this is C minus N. C minus N. C minus N. So this is, so what is this? This is just, this is minus C minus N. This is Cn is equal to Bn, right? So you add them together. It's just a simple calculation. So 2Cn is equal to An plus Bn, or Cn is equal to An plus Bn over 2. 1 plus, come on. Let me just. Okay, so we have this one. Okay, let me write this as it is. Minus JC minus N plus JCN is equal to Bn. Okay? So you multiply this with J, then you have here Cn, C minus N plus Cn is equal to An, and this becomes minus J square C minus N plus J square Cn is equal to J times Bn. Okay? And that is equal to C minus N plus Cn is equal to An, and this is equal to C minus N minus Cn is equal to JBN. You now subtract this, okay? This will cancel, then you have 2Cn is equal to An minus JBN, and Cn is equal to, I just want to show you the interrelationship, okay? So if you have An and Bn, so if you start from here, and you already computed your coefficients, to obtain the complex Fourier series, you don't need to do anything extra. You just add them together, and in this manner, and you have it, and vice versa, right? We will use this. Any question? When there is no question, that means problem, okay? So you should ask questions and comments. C minus N. So I subtracted this, so these two canceled. So since I am subtracting, this is like multiplying, this is minus 1. So it became 2 CNs, okay? Okay. Now, let's continue with this one. Okay. Now let's look into some special cases of functions. Even function and odd function. So what is an even function? Even function means it is, of course, if f minus t is equal to ft. Okay? So you have function here. Whatever is happening for t, let's say it has this function has this value. For minus t, it has the same value. For example, this is an even function, okay? Or this is an even function, whatever. So whatever the value you have for plus t, you have the same value for minus t, okay? So odd function is f minus t is equal to minus ft, okay? This is like whatever the value of the function is here, this is for t, for minus t, it is the opposite value here, okay? Let's say, like this x cubed, right? So the value here is the same as here, but it has just sign difference, okay? So if I say the following, every function is either or odd, is this true? Of course not. But can I write every function as a summation of even part and odd part, right? How did I do that? I told you that in the first week, right? So I don't want to, I just want to focus on this and let's see what happens to this. For an even function, let me calculate for an even function. Meaning xt is equal to x minus t. Let me calculate Bn, the coefficient, Fourier series coefficient of sine n omega 0 t. Okay, let's see what happens to this one. So what was this? That's 2 over t from minus t over 2 to plus t over 2, xt sine n omega 0 t dt, isn't it? So let me separate this into two parts. 2 over t from minus t over 2 to 0, xt sine n omega 0 t dt plus 0 to t over 2 xt sine n omega 0 t dt. Here, let me make a change of variable. This is t here is dummy variable, isn't it? So let's say I replace t is equal to minus u. So what happens to this integral? Let me just write this here, okay? This part only, I will keep that as it is. So this is 2 over t. Okay, what happens to the lower limit? Huh? U, what happens to this one? For t equal to minus 2 over 2, what is the value of u? T over 2, right? And 0 remains as it is. And this becomes x minus u. Since it is xt, it's x minus u. Okay? Then this sine n omega 0 minus u, right? And this is dt is minus du. So calculus is good, right? It's not a useless thing. It's important. So what is this equal to, since this is an even function? Huh? xu. And this is minus sine n omega 0 t. Okay? And this is minus du. So you have u, of course. So you have minus and minus, it's plus. Okay? I erase these two things. Then can I flip this? What will happen? Minus. Okay. So this integral turned out to be equal to this one. Okay, let me write it clean here. Minus 2 over t, 0 to xu sine n omega 0 u du. What is the difference between these two? This is, of course, 2 over t here. They are the same, right? Just this is minus. So what happens is they cancel each other. So just with the knowledge that the function is an even function, without knowing anything else about the function, we are able to say that for such functions, bn's are equal to 0, right? That's important. How about an's? Of course, an's are not equal to 0. A0, it doesn't have to be equal to 0. It could be or not. Okay. Now, I'm not going to do it, but tell me, if it's an odd function, what is your guess? ANs will be 0, and A0 will be 0, right? Yes. So the result is one for even functions, of course, for even periodic functions. Of course, to talk about Fourier series, it has to be a periodic function, right? So I'm not saying that we are in the domain of periodic functions. That's why I'm not explicitly saying that. Functions Bn equal to 0 for all n. 2 for odd functions an for all n. Good. So it's always good to look at your function and see if it is a special case. If it is even or odd, great. You can just go ahead and do it, right? You can just go ahead and calculate. If it is even function, you say there is no need to try to find out what is Bn, what are Bn's. If it is odd function, say there is no need to look for A0 or An. Just forget about them. Okay. Okay, I want to now tell you about Parseval's theorem. It is an amazing theorem, and it has an excellent interpretation about what Fourier series is and how it affects really telecommunications. Parseval's theorem is about the energy distribution in a signal, okay? So basically, let's do the following. What is this? This is the energy of the signal in one period, isn't it? So this is the energy of the signal from beginning of the period to end of the period. It could be 0 to t or just in one period. During one period, how much energy you have in a signal, okay? So what we do is that what is x of t? It is written given here, right? X of t is, so let me write this as x of t and x star of t dt. This means complex conjugate of x of t. This, you know, multiplying a complex number with its conjugate gives you the absolute value squared, right? So this is equal to x of t is n equal, where do we have it? Here, right? N equal from minus infinity to plus infinity, Cn e to the j n omega 0 t. This is x of t. And x star of t is, so n equal, m equal from minus infinity to plus infinity, Cm, right? E to the j m omega 0 t, complex conjugate. So that's going to give me what? Minus t over 2 to plus t over 2, n equal from 0 to infinity, Cn e to the j n omega 0 t. And this complex conjugate, what does that tell me? M equal from 0 to infinity, I'm sorry, minus infinity to plus infinity. And complex conjugate becomes CM conjugate, and this is e to the minus jm omega 0 t. Are we together? Please, let's work together. Okay? So I encourage you to follow what I am doing because video is there. You can watch it again and complete your notes. But it's very important that when I ask questions, I get answers. Okay? Otherwise, it's like talking to the empty class and making a movie of it and just broadcasting it, right? So please participate, and you can just complete your missing notes at home. Right? So we will do the same trick. We'll just move these summations to the beginning and integral to the front. It will not change anything, isn't it? So we say n equal from minus infinity to plus infinity. M is equal minus infinity to plus infinity. Cn, Cm conjugate e to the j omega 0. So you have n omega 0 t minus m omega 0 t. So you bring them under same exponent, n minus m t. Okay? You know what this is, right? We just did it a minute ago. What is this equal to? This integral is equal to 0 if n is different from m. It is equal to, when n is equal to m, this is 1. This integral is equal to t if n is equal to m. So the whole thing becomes, this is equal to n equal from minus infinity to plus infinity Cn conjugate times t. What is this? This is just t times Isn't this beautiful? So let's write it like this. So in general, we'll take this t here. So 1 over t minus t over 2 to plus t over 2 x squared t dt is equal to okay, I will put this here, okay, and I will just wait for 1 minute so that everybody really looks at it and thinks about it. Then I will ask for your opinion. What is the physical interpretation of this beautiful expression? Let me see who is going to have the best interpretation of this. So we have a periodic signal. We made Fourier analysis of it, and we came up with omega 0, 2 omega 0, 3 omega 0, all omegas, okay? Then, so we now know which harmonic is represented in the signal by how much, right? What is that? That corresponds to your Cn's, right? So every harmonic has an exponent, and it has a coefficient, Cn. So what does this tell you? You're talking about the energy of the signal. So you have a periodic signal, and the total energy of this is this, and you just divide this. So this is just average power at any given point is this. So what is this telling you? Okay, who would like to interpret this? You can say something wrong, it's okay, but please try. Okay, Albanian, what does it mean? What's your name? Huh? Hornekta. Okay, Hornekta. What does this mean to you?
Maybe the energy of the signal is related to the period.
It is, of course, related. What does this mean? What this is telling you is that the energy of the signal is shared between the harmonics. And this share of, let's say it has 3 harmonics, right? C1 and C7 and C100. 3 harmonics only in the signal. And total energy of the signal is just square of these coefficients of these harmonics. Okay? So this is telling you how much of the power of this signal is in which harmonic exactly. So this is an energy and power thing, right? So this is telling you exactly how much of energy of your signal, your periodic signal, is stored in which frequency. Isn't that? It's just beautiful. This is not an approximate thing. This is just equality. Okay? So time domain energy of it is equal to the just sum of the squares of the Fourier series coefficients. This is really wonderful. It's not. It is not equal. For example, yeah, this is a good case. So this summation, why is it going? This is energy in one period, right? Minus T over 2 to plus T over 2. How can it be infinite? Of course, it could be infinite as well, right? You could just an outrageous signal going to infinity in one period. Do you realize this? This is the whole basis of telecommunications and controls and everything. Okay, this is telling you, this is really analyzing the signal in details. You are not, by using Fourier transform, you are not only finding out which harmonics exist in your signal. What else you are finding out? You are finding out how much of energy is carried by which harmonics. Okay, this is what it means. Parseval's theorem. Who understood it now? Okay. The others, please tell me, where did you get stuck? What is the confusion? Please. Okay. Last week we calculated a Fourier series for this function, if I am not wrong. Before that, I want to also tell you, how about Parseval's theorem in terms of the others, okay? So it's very easy. So how about in terms of A0 and ANs and BNs, what is Parseval's theorem? So how about in this case, right? A0 plus so in terms of this A0, AN, and BN, what is Parseval's theorem? So we just obtain it directly from here, okay? So you have 1 over T minus T over 2 to plus T over 2, x squared T dt is equal to n equal from minus infinity to plus infinity Cn square. And what was Cn in terms of AN and BN? What was that? AN plus. So I will write this as, I'm sorry, first step is you write this again, n equal from minus infinity to minus 1 Cn square plus n equal from 1 to infinity Cn square and C0 square. Okay, this is what it is. So here, I just replace n by minus n, so I obtain, okay, m equal from 1 to infinity C minus m square of course, this is the same as, since you are talking about absolute value, this is same as okay, so this is twice n equal from 1 to infinity Cn square plus C0 square. Then what was this? Twice. So what is Cn? Cn, if I am not wrong, An minus JBN over 2, right? So this is real, this is real, this is real. So what is absolute value of Cn squared? What is that? 1 over 4. What? An squared plus Bn squared, isn't it? So you just substitute here. So n equal from over 1 to infinity An squared plus Bn squared over 4 plus C0 squared. So what is that equal to? So this 4 comes out, so you have 1/2 n equal from 1 to infinity An squared Bn squared plus n A0 was the same as C0. So this is Parseval's theorem in terms of sinusoids, okay, real sinusoids. So you just take squares, add them up, and go from 1 to infinity, and divide the rest by 2. Okay, this is Parseval's theorem in terms of cosines and sines. Isn't this beautiful how they are totally related? Of course, you could directly derive this as well. So it doesn't have to be this way. It's much more messy. You would have cosines and sines and sines and sines and cosines, and use trigonometric identities and calculate those integrals, and you would arrive at the same thing. Okay? Okay. We did an example, and I want to continue on that example. We said that if we have an odd function, did I say this was this pi and minus pi? This was -1 and 1. Is this the example I did? Can you check your notes? Anyway, so we found out that this t and x of t, of course, this x of t, what is the period here? This is a periodic function with period 2 pi, right? Okay, and we found out that x of t is equal to 4 over pi sine x sine 3x over 3 sine 2n plus 1 x 2 continues like that. So it's an odd function, but it still doesn't have all of the signs as well, right? Sine 2x is missing. Sine 4x is missing. So you have only sine x, sine 2n plus 1x over. So this was the Fourier series expansion, right? Now we learned about Parseval's theorem. So let's calculate what this means in terms of Parseval's theorem, okay? Let's see what it will give us. So what does it tell us here? So this is, what are ANs here? A0 is also 0. So A2n plus 1 is equal to 1 over 2n plus 1, right? B2n is also 0. Okay, this is the only non-zero one. Times 4 over pi. 4 over pi is also there. So Parseval's theorem is telling me that, okay, so 1 over 2 pi, this is t, 2 pi, minus t over 2, so this is 2 pi over, so this is minus pi to plus pi, x square t So what is the square of this? What happens to when you take square of this? This remains as it is. It is just flips over here, right? What is the integral of this? So this is base is 2 pi, and the height is 1, so 2 pi. So that's 2 pi. And that is supposed to be equal to now, this is the left-hand side of that, is equal to 1/2 n equal from 1 to infinity. And ANs are 0, so BN, so n is equal to 1 to 4 over pi times 1 over 2n plus 1. Now square, and this is also square, isn't it? Those of you who love number series, you see a miracle here is happening, right? So you have, just bring this out. So this is 1/2 16 over pi squared is equal to, so times n equal from 1 to infinity 1 over 2n plus 1 squared is equal to 2 pi. So this becomes 8, and this will go there. Okay. So you have then this series summation is equal to n equal from 1 to infinity 1 over 2n plus 1 squared is equal to pi cubed over 4. Okay? So since Parseval's theorem, we proved it is true, it just gave us the summation here, right? So we obtain the result of this infinite sum. It just came out as it is. So it has to be pi cubed over 3. Okay. This might be an 8, but I couldn't find it here. So if I will just tell you that when I find out. Okay? Let's give a break. Okay. You want to tell me something? Okay. So we want to find the Fourier series for this x of t. What can you tell me about this? It's an even function. Excellent. So there is no need to look for bn's, right? So what is an? What is a0, first of all? A0 is from minus pi to pi x of t dt. So what is that equal to in this case? So this is pi. So pi, by the way, here, this integral is 2 pi, right? What we have here is 1 divided by 2 pi. So the result is 1, not 2 pi. Okay, that was the problem. So therefore, this summation, which is equal to this, is equal to 1. So that just goes, so this summation is pi squared over 8, not pi cubed, okay? So during the break, I just realized that. So this also shows that, unfortunately, you couldn't also catch it, so you should be careful. You should try to find out if I'm making any mistake, you should just catch me. Okay, good. So this is pi squared over 2. So the other one is here, so it is pi squared. Right? So A0 is pi squared here. Right? So 2 pi. So pi squared over 2. 2 of them, so it is pi squared. AN is equal to, so this is what? This was 1 over 2 pi times this. So this is 2 pi, so this is pi over 2. So we should be careful about these little details, okay? So this is pi over 2. So this is 1, this is 2 over, so this is 1 over pi times from, then what is going to happen now? Let's just ignore that it is 1 over 2 pi, and this was what? This was 2 over t, so this is 2 over 2 pi, right? What was A0? Where is our A0? A0. A0 is A0 is 1 over 2 pi, and AN is 1 over pi. Okay, this is 1 over 2 pi. So therefore, this is 2. So this is 1 over pi minus pi to pi. And what is this function? So this is x of t and cosine and omega 0 t dt, right? So we divide this into two portions, 1 over pi times, so minus pi to 0 x of t cosine here again we make change of variable, t is equal to minus u, okay? Then this will become from pi to 0 x minus u cosine minus n omega 0 u, and this is minus du. This is just equal to cosine n omega 0 u, right? This is just xu because it is an even function. This minus, and I flip this, it gives me exactly this one, right? So this is 1 over pi. So I have here 2 over pi from 0 to pi x of t cosine n omega 0 t dt. Okay? And what is that integral? So 0 to pi. What is x of t here? It's just t, right? For t equal to 0, it is 0. For t equal to pi, it is pi. So t and cosine and omega 0 t dt. How do you compute this integral? How do you do that? Yes, excellent. Integration by part. So you call this u, and you call this v prime. So u is t, u prime is 1, v prime is cosine n omega 0 t, and v is, what is v? 1 over n omega 0 sine n omega 0 t. So this integral is equal to u times v. So t times 1 over n omega 0 sine n omega 0 t from 0 to pi, okay, minus this times that. So minus 0 to pi 1 over n omega 0 sine n omega 0 t dt. Okay, what is this? In upper limit, sine n omega 0 pi. Omega 0 was what? Period is, so it is, so period is 2 pi, so t is equal to 2 pi, omega 0 is 2 pi over t. So what is omega 0? 1. Okay, there is no omega 0. Omega 0 is equal to here. In this example, omega 0 is 1. T is equal to 2 pi, right? So this is sine n pi. It's always 0. And the lower limit, you have t here, so this has no contribution. Okay, so this is 0, so you have here minus 1 over n omega 0. I'm not going to answer your questions, by the way. Okay? So you just came in, you should come in the beginning. 0 to pi sine n omega 0 t dt. So what is this integral? So this is derivative of what? Cosine n omega 0 t, right? So this is minus 1 over n omega 0, 1 over n omega 0, cosine n omega 0 t from 0 to pi. Okay? So this is minus. So this is 1 over, omega 0 was 1, okay, I'm sorry, this is 1 over n squared times cosine, this is 1 again, cosine n pi is minus 1 to the, so cosine, let me write the cosine n pi minus 1, okay? So this is 1 over n squared, this is minus 1 to the power n minus 1. Okay, so in that case, an is equal to 2 over pi times 1 over n squared minus 1 to the n minus 1. In other words, let's write it like this. For n equal to 1, this is 0, right? For n equal to 2, this is 2 pi times minus 2 over n squared, right? For n equal to 1, it is minus n, 1, okay? Over 1. For n equal to 1, it is, for n equal to 0, there is nothing. You cannot have it. N equal to 0, a0. For n equal to 1, it is 2 over pi times minus 2 over 1. Okay, the next term, 2 over pi times, this is, for n equal to 2, this is 1, this is minus, this is 0. So that term is 0. For n equal to 3, that's again minus 2 over 3 squared, right? So general term will be minus 4 over pi 1 over 2 n plus 1 squared. This is the general term. So A2n are equal to 0. A2n plus 1s are equal to minus 4 over pi 1 over 2n plus 1 squared. So these are the Fourier series coefficients. Of course, bn's are all 0. We didn't compute them even because it is an odd function. Now let's apply Parseval's. First of all, so what do we have now? We have, for example, what did we find out? Let me write the expression here. So for that function, x of t is equal to a0, which was, what was a0? Pi over 2 minus 4 over pi n equal from 0 to infinity 1 over 2n plus 1 over 2n plus 1 times cosine 2n plus 1 x, right? Yeah, I'm just thinking about that. Let's see, I mean, it should be this. For first term, for n equal to 0, I should get this one, right? For n equal to 0, this is minus 4 over pi. For n equal to 1, I should get this one. So I'm re-indexing my series, right? For n equal to 1, this is going to be 4 minus 4 over pi. It's fixed, so 1 over 3 squared. So it is right.
N is equal when it is 3.
So the odd ones are 0. So I am just eliminating the odd ones. So for A2, A4, A6, they are all equal to 0. So I could call this K, 2K plus 1 to make it more understandable. That's what I should have done, okay? But since it's dummy variable and you are very smart people, I just take it, rename it, take this liberty and rename it as n, okay? Thank you very much for pointing that out, because I'm sure it helped many people to understand. Okay, so then this is the Fourier series expansion that we have for this. Okay, we have only these harmonics in it. So we don't have 2x, etc. Okay, so let's just again make use of this series and obtain a summation. For t equal to 0, what is the value of the function? 0, right? So x0 is 0. Okay, that is equal to then, so this 0 is equal to pi over 2 minus 4 over pi n equal from 0 to infinity. This is supposed to be square, isn't it? I'm sorry. Square has to be there. 1 over 2n plus 1 square. And what is for x equal to 0? What x? This is t. This is t. So this is cosine 0 is 1. So therefore, this is what it is. So that gives you 4 over pi in other words, oh, this looks familiar, doesn't it? We got it from here as well. But we got it by applying Parseval's theorem to it. We applied Parseval's theorem to the Taylor series, to the Fourier series expansion of this function. Now, when we obtained the Taylor series expansion for that function, which is integral of that, by the way, we were able to obtain this summation again from here. Well, let's now apply since now we have this Fourier series expansion for this function, let's apply also Parseval's theorem on this. And let's see what we get. So Parseval's theorem tells us again, okay, so I have A0 is equal to pi over 2, A2n plus 1 is equal to 4 over pi minus 4 over pi, 1 over. You see, all the coefficients are negative, except the first one. Okay, so it's very interesting. It's a very interesting Fourier series extension. And A2n equal to 0, Bn is equal to 0. Okay? Now Parseval's theorem tells me that 1 over 2 pi times minus pi to pi x squared t dt is equal to 1/2 times n equal from first A0. A0 squared, did I have there a 1/2? So I never memorize anything. This, huh? A0 squared, yes, it was the same. I remember Cn squared, yes. Plus 1/2 times n equal from 1 to infinity an squared. Since it's just real, there is no need for absolute value. An squared, okay? So what is this left-hand side other than 2 pi? So what is this square of this? If you take square of this, so this is now, it becomes t squared. Okay? So t squared. Integral from minus pi to pi. Can I say that this is twice integral from 0 to pi x squared t dt? I can say that, right? It's an even function. Therefore, what is the function there? It becomes t squared dt, 0 to pi. So it is 2 pi cubed over 3. This is t cubed over 3 from 0 to pi. So that is 2 pi cubed over 3. And this integral becomes then, we will divide it by 2 pi. Okay? So this integral 1 over 2 pi times minus pi to pi x squared t dt becomes 2 pi cubed over 3 times 1 over 2 pi. So these two cancels. This becomes, so it is pi squared over pi squared over 3. Okay. So this we now know the left-hand side. So what is right-hand side? A squared. What was a squared? This was pi over 2 squared, isn't it? And this 1/2 times n equal from 1 to infinity, and then this is 4 over pi minus 4 over pi squared, 1 over 2n plus 1 to the power 4. So it is equal to pi squared over 3. So we take this to the other side. So 1/2 n equal from 1 to infinity. This is so 16 over pi squared. 1 over 2n plus 1 to the power 4 is equal to pi squared over 3 pi square over 4, which is pi square times pi square over 12. Okay? And take this to the other side, so n equal from 1 to infinity, 1 over 2n plus 1 to the power 4. And this is 8. This is over 96. So this just comes out free. Isn't this beautiful? So in complex variable theory, you find amazing ways of computing some summations of numerical series. Okay, it just comes out so easily, isn't it? Just because of something we proved and we are sure of it. That's it. Okay. So, of course, you should do some exercises. I'm going to give you a homework set tonight. I gave the draft to Ahmed. He's going to type it and he's going to put it on the website tonight so that you can solve those questions. Next week, the first class, we'll have our quiz. It will be something 30 to 45 minutes. After that, we will continue our class. And we will see if that big classroom is available. Okay, so that everybody can fit in the class. Okay? Okay. I was going to start Fourier transform today, but I'm not going to do it. I want to do it when you are fresh. But I want to tell you a few more beautiful things about Fourier series and its implications. Okay?
Is it energy? I get this right.
This is a corollary. This is not the energy. This is summation of this series. So energy is this. That is equal to that. Okay? So that tells you that integral of square of the signal in one period and divided by 2 pi, so the average energy, which is the power, average power of the signal, is equal to summation of all these harmonics. Okay? So it has this much of DC, and it has every harmonic, so it just drops very fast, isn't it? So the energy that is stored in every harmonic, when n grows, it just very quickly will drop. It's just power 4, right? So when you have like when n is equal to 3, this becomes 1 over 7 to the 4. So it just becomes very, very small. So it is concentrated in the first few harmonics. Any questions? So you know how to obtain a Fourier series for a given periodic function and how to obtain Parseval's relationship between energy and the coefficients, etc. Okay? Now, what does this mean? Linear time invariant system. So it means a lot, right? So let's take a signal, a special signal. Xt is equal to the e to the st. Okay? So our input signal is e to the st. And let's calculate the output of our system for this signal. What is that? And we know, of course, the impulse response. Okay? Impulse response is something that is available to us. You know what is impulse response, right? So what is yt in terms of the impulse response? Minus infinity to plus infinity, then h tau e to, so this is e to the s t minus tau d tau, right? So let's separate this into two parts. This e to the st. Can I take this out of the integral? Integral with respect to tau, right? This is like a parameter. So I can move this out. So I have then minus infinity to plus infinity, h tau, e to the minus s tau, d tau, and so there is, so let me call this is what? This is just, let's call s as a parameter. Can I just call this result of this integral is a function of that parameter, h of s? Okay, so I use the little h for time domain. So I take this integral, so let me call this h of s. So for this input, when the input is e to the st, output is h of s. Okay, what's going on here? From linear algebra, does it remind you something? What is this? Can I call e to the s an eigenvector? Then what is the eigenvalue corresponding to that? It is h of s, right? So this system, so this is a linear operator, okay? It's like a matrix. When the input is e to the st, the output is also e to the st. So it comes out, so it goes in and comes out as it is. It is multiplied by a factor. So it's like similar to eigenvectors and eigenvalues, isn't it? So these exponential functions are eigenfunctions of linear time invariant systems. So they are extremely important, okay? So S in general, for example, this x of t could be e to the 2t, okay? Or it could be e to the j omega t. It could be e to the 2 minus j omega t. It could be just any complex number, right? Okay. Now, this is, of course, something very, very, very important. So next week, when we talk about Fourier transform, and after we finish that, I'm not going to spend too much time on Fourier transform because right after that, we will talk about Laplace transform. As a matter of fact, this is two-sided Laplace transform. Who has seen Laplace transform before? Where did you see it? Which course? Differential equation. Okay. Of course, this is two-sided Laplace transform. So, okay, so it's so naturally, it comes into the picture that when you have the input is a complex exponential, it just comes out and then multiplies the parameter. So you could just calculate this. If you have h of s as a parametric function, then you could just take e to the s1t as one signal. Let's say this is x1 is this. Then the output is hs1 e to the s1t. You have another input e to the s2t. Then the output would be etc., right? So if you have a linear combination of this alpha times x1 times beta times x2, since this is a linear time invariant system, what will be the output? It will be alpha times hs1 e to the s1t plus beta times hs2 e to the s2t. Okay? So on and so forth. Okay? So I will just call this ht. Okay? So if I have sine omega t, I have a response Let's call this y1t. And I have another one. Let's call this cosine omega t. And the output is y2t. If my input is, if I make a third hypothetical experiment now, cosine omega t plus j sine omega t, okay? What am I supposed to get here from linearity? So this is, of course, I have a real input, a real system. The output is, of course, real, right? So y1t sine omega t will give me, the system will generate an output corresponding to that. If I take cosine omega t, I will get another output. Since this is a linear time invariant system, I always, so it doesn't change by time. So if I were to make a third experiment and take a linear combination of them, so this is like alpha is equal to 1, right? This beta is equal to j. So this is like e to the j omega t, right? But I already obtained the output corresponding to each one. So the output will be what? From linearity. y1 plus j y2t, isn't it? Isn't this? Vice versa, yes. Okay. y2, I should have done it. Okay, y2t in other words, what would be another way of doing it? If I have this is h of t again, I could just, of course, in engineering design, we are working with our paper and pencil, so it doesn't have to be a pure physical input. So we could have inputs like this, as we did in Fourier series, right? So we can have e to the j omega t as our input. And the output will be, again, a complex output. So complex input will give us a complex output. But we know from here that if I have e to the j omega t, if I take the real part of this, it will be the response of my system when the input is sine omega t. If I take the real part of it, it will be the response of the system when the input is cosine omega t. Okay? And if I take the imaginary part of it, if I take the imaginary part of the output, that is the response of my system when the input is sine omega t. Isn't this very beautiful? And you will use this a lot, everywhere, in circuit theory and everything. I'm sure you already started using this, okay? So this is how you do steady state analysis of circuits, for example. Okay. What else I want to? Of course, this is going to be, what is this going to be? H S is here what? J omega e to the j omega t, isn't it? Let me just do an example on that one here. Let's say my impulse response is e to the minus s t e to the minus t ut, okay, e to the minus t ut. This is my impulse response of my system. I have a system, okay. This is ht. Input comes in and outputs go out, okay. Ut is unit step vector. It is 1 when t is greater than or equal to 0, 0 otherwise. Okay? And when an impulse response is 0 for negative t, what do we call those kind of systems? Huh? Causal systems. Yes, thank you very much. Yes, it is causal system. So this means for this kind of systems, to be able to compute the output of the system right now, you don't need to know the future inputs, okay? If it is not like that, if the impulse response of the system is not 0 for negative t, that would require, to be able to obtain the output of that system, now you would need to know the future inputs, okay? That would be predictive system, okay? Okay, so let me just compute this h of s guy. So h of s is minus infinity to plus infinity, h tau e to the minus s tau d tau, right? So h tau is, since it is 0 for negative t, so this is from 0 to infinity e to the minus tau, e to the minus s tau d tau, which is 0 to infinity e to the minus s plus 1 tau d tau. So that is minus 1 over s plus 1 e to the s plus 1 tau from 0 to infinity. So this is equal to, in the upper limit, this is equal to 0. In the lower limit, this is equal to 1, provided s plus 1 is positive. Real part of s plus 1 is positive, right? Otherwise, this will explode. If it is negative, it's going to explode. So this is equal to, so this h of s is equal to 1 over s plus 1. So this is like the eigen value of our system that has this impulse response, okay? For every s, for any input with e to the st input, you will have, it will be multiplied with this number and it will come out exactly as it is. Let me explain what it means in terms of frequencies, okay? So let's say s is equal to j omega, okay? So it is just some frequencies. So input xt is e to the j omega t. So it is cosine omega t plus j sine omega t. So what we are saying is that if the input to my system is a sinusoid, a combination of cosine omega t, sine omega t, or whatever, I'm taking both of them together because it's very easy to analyze. If I'm just wondering about the response to the cosine omega t, I will just get the result and take the real part of it. It's so easy, isn't it? So mathematics makes it very easy for us to be able to obtain. Otherwise, to get, so this is not an eigenvector of my linear system. Cosine omega t is not an eigenvector of my linear system. Sine omega t is not as well, but e to the j omega t is. So I'm very easily able to compute the response of my system to this very special input, and just getting the real part of it or imaginary part of it, I'm able to obtain these things. So it's just miracle. So we owe a lot to people who invented all these observations and made it electrical engineering what it is today, right? It's just marvelous. We are so powerful because of all these very valuable tricks and inventions. Okay, so when input is this, input x of t is equal to e to the j omega t. What is the output? Output is h j omega, right? We did it there. So whatever is here, j omega is st, that comes in here, right? Times e to the j omega t. Isn't that beautiful? So let me see now. So this is, I should write this here. So this is YT, right? This is YT. It's a complex output. It's hypothetical complex output, right? So let me calculate absolute value of YT. What is that? It's equal to H J omega absolute value times, what is the absolute value of this one? Absolute value of e to the j omega t. What is it? 1. Just 1, right? So this, remember, any complex number can be written as r e to the j theta, right? So this j theta is just unit circle. When theta changes, this is just 1, minus pi over 2, etc. Okay, I'm sorry. Minus j, okay? It's just unit circle, okay? So this magnitude is 1. So this is equal to. So what is it doing? Really, when you have an input, and this is like you can call normalized input, you have a signal with amplitude 1, and the amplitude of the output just depends on the system. A characteristic of the eigenvalue of the system, for the time being, let's call it eigenvalue of the system for that eigenvector, right? How many eigenvectors does my system have? Infinitely many, right? Any e to the st is an eigenvector for my system. Great. So h of s, we found out that it was 1 over s plus 1 for any s, right? When s is equal to j omega, this is equal to 1 over 1 plus j omega. So what is the magnitude of h j omega? That is 1 over. Let's see what this system is doing to the signals that are coming in. Okay? When omega is 0, it's saying that if a DC coming in, if there is no change, it will just go out as it is. I'm not going to touch it. Okay? There is no frequency involved. This is just no change in your signal. It can just go out. I'm not going to change it at all. Okay? When, let's say, omega becomes 1, what happens to this? This becomes 1 over square root of, so this is 1. Then omega equal to 1, this becomes this value, right? When omega equal to 2, this becomes 1 over square root of 5, okay? So basically, it's going to have this kind of character. Okay, this is so depending on your frequency of your input, this system will change the magnitude of it. Of course, it will change the phase as well. Okay? So it is not going to change the frequency of your signal. So whatever frequency is going in will come out exactly as it is. Okay? It's a linear time Morse system. But it's going to change its magnitude, and it's going to change its phase. And this is a filter. Okay? This is what we call a filter. Okay? So we design systems that we say, okay, there is some noise around here. Okay? Some things are happening in those frequencies. I don't want to see them. So you design a system, an electronic system, such that it will pass the frequencies you want to pass with no problem, without changing them, or amplify them if necessary, if you have an active filter. And it will, in the other frequencies, whatever comes in, nothing will come out, or very little will come out. Okay? So we design a system that discriminates against the signals that are coming in. It will pass some frequencies. It will pass some bands of frequencies, of course. We don't do it one by one. It is very difficult. We say that my system should pass these bands, let's say 3.4 kilohertz. Okay? And after that, it should stop. This is my ideal filter characteristic. Anything below, this is frequency, okay? And this is the magnitude. Anything below 3.4 kilohertz, it should just be multiplied by 1 and pass. Anything above that should be multiplied with 0. Okay? So you would design a system, a linear time univariate system that when you calculate HS of it, then it would have this kind of frequency characteristic. These are called filter. Sometimes this is a low pass filter. Sometimes you say that, okay, I want to have a filter that suppresses the low frequencies, okay? There is too much, my power grid, noise, etc., that I don't want to see them, okay? I want to kill them, and I just want to pass above some frequencies. Anything below that should be suppressed. This is how it works, okay? This is the interpretation of linear time invariant systems as filters. I think enough for today. You had enough of it. So please prepare well for your quiz next week. We will start with the quiz and continue.